Hi, good evening everyone. We are now on the topic of wave phenomena. Now we're going to focus on three phenomena, or what waves can go through. I think previously we have talked about reflection slightly, reflection of light. We've also talked about slightly on refraction of light. Now today we are also going to look into what is known as diffraction, something probably you have not heard about, but yeah, we're going to cover diffraction as well. Now we're going to focus our attention today on water waves, alright? Now, and how water waves will undergo reflection, refraction, and diffraction. Now, but before we go further, we need to consider what is known as wavefronts. So you can see this is what water waves will look like. We have what is known as here, we got peaks as the topmost point. We've also got trough as the lowest point, right? Now what we can do is if we are looking from the top, of our top view, what we will have is we will look and we'll see an image that looks something like this, right? We've got the peaks, we've got the peaks, we've got the peaks, we've got the peaks. Now, of course, we have, so we can label this as peaks, 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 and peaks. Now, I'm going to draw dotted lines to represent troughs, represent troughs, represent troughs. Alright, so this is T, T, and T. So, now if you look at these lines, we have, this is known as a wavelength. And the wave in this case is moving from the left to the right. Direction of travel of wave. Right, so the wave is traveling from the left to the right. Now what is crucial here is for us to recognize direction of wave is perpendicular to its wave fronts. Right. Now we got the wave fronts here. We got the wave fronts here. These are wave fronts and wave fronts. Now this, if we draw a 90-degree line, 90 degrees, 90 degrees, we will get the direction of the wave. Alright, again we're going to apply this shortly with regards to direction. Now we apply that when it comes to reflection of waves. Now what we have here is we have water waves traveling from the bottom upwards, and it will hit a reflector. So I'll just label this is a reflector. It could be a wall or something. So what we're going to do is we're going to try to draw the wavefronts of the waves after reflection. Now to do that, what we need to do is number one, draw direction of incident wave. Alright, so if you've got your pencil, you need to take your pencil and draw a line that's 90 degrees. So this is 90 degrees, very crucial to be exact here. Now, step number 2, draw the normal to the surface of the reflector. Alright, so what we need to do is, now in 90-degree line, the normal line, you draw the normal right here. This is a normal. Right. Now thirdly, now because this is reflection, we need to apply the law of reflection, or I is equals to R. Alright, now to do that, protractor comes into play. So we measure the angle right here. In this case, from 90 down here is 10, 20, 30, 37, right? So I got this is 37 degrees. Now what that means also, I will need a angle of reflection to be 37 degrees. So I just get my protractor out. I'll mark 10, 20, 30, 37 is right here. With that, I will draw a line in this direction. Alright. Now fourthly, you need to draw reflected wavefronts. Now very crucial, during reflection of waves, we need to remember, we need to apply I is equals to R, and to keep the wavelength constant. Alright, so now what does that mean in this case? Now what we'll do first is we draw one wavefront. Right, this is 90-degree line. So this is one of the reflected wavefronts. Now following from there, we will need to make sure that the wavelength is constant. So what I'll do is I'll take a ruler, I'll measure this. Now in this case, if you look at it, this is 1 centimeters. Okay, the wavelength is 1 centimeters. Now what that means is I need to have the reflected wavefronts to be 1 centimeter as well. So I got 1 cm, 2 cm, and draw a third one, 3 cm. Again, all of them must be perpendicular to this arrow. So I'll draw this line. Draw this line. Finally draw this line. Right? So all of these are perpendicular to each other, and lambda is equals to 1 cm. So this is what we will have when water waves hit a reflector and it bounces off. We need to apply I is equals to R, and remembering to make sure that wavelength remains constant. Now following on from that, we've got refraction of waves. Now similar to what we have covered in our previous lesson, refraction of waves involves change in wave speed. Now because of the change in wave speed, there will usually be a change in direction. Now in a short while, hopefully it will make sense in a short while, but wavelength will change as well. Alright, now so what does it mean when we want to draw the wavefronts when waves are undergoing refraction? Now we need to firstly identify whether the speed is increasing or speed is decreasing. Now for how I remember is shallow is where the wave travels slow and the wavefronts are short. Right? Shallow means slow and short. Now deep, of course, will then mean fast and long. Alright? So keep that in mind as we start drawing the wavefronts. So firstly, similar to the previous example, we need to draw a line 90 degrees to this wave. Alright, now what this means is the wave is traveling in this direction. We need to have the normal line 90 degrees to the surface. This is known as the normal line. Right? Now from there on, from moving from fast to slow, what will happen is it will bend, the change in direction, it will go towards the normal. Now how far towards the normal, it's not really important to get the values or angles exact, but what is crucial is for you to show that it does bend towards the normal. So in this case, what I'll do is I'll draw a line in this direction. Alright, now following on from there, we need to draw the refracted wavefronts. What I'll do is I'll draw a line here. Alright, that's our first wavefront. Now we need to draw the subsequent ones. Now remembering the wavelength is now shortened. Now what that means is, again, we do not know have to be exact in terms of ratio. What it must be apparent is the wavelength here, incident, and the wavelength here, reflected. Wavelength I must definitely be I. Alright, the wavelength must decrease. Now, keeping that in mind, draw the next line. Alright, so this is where we get our, okay, it's not, I need to change that slightly. Now this is why we use a pencil. Need to make sure it's 90 degrees. Right. There we go. Ooh. Right, so that's our refraction of waves moving from deep to shallow. Now very quickly, let's just do the next one. From shallow into deep, remembering shallow means it's slow and short. Alright, now what will happen is as it goes to deep, the speed will increase and the wavelength will be longer as well. So, similar to what we have done previously, we need to draw the direction of wave. Now, you can draw right the center or just along the way is fine. Right, this is 90 degree, making sure, okay, we draw the normal line. Now here, because it's moving to a faster region, what will happen is it will bend away from the normal. Again, the angles doesn't have to be exact. You just need to make sure that it's apparent that it's bending away from the normal. Right? So next, we need to draw the refracted wavefronts. Here I've got one. Now I got this, the incident wavelength, sorry. Now what I need to do, make sure that the refracted wavefront is larger. So in this case, what I'll do is I'll draw something that looks like this. I'll draw the next one looking something like this. Alright, now in this case, you should try to make sure that these two is roughly the same. Right, it's better if you did actually measure it, but if you look at this, it looks by eye to be approximately the same. So this is essentially what we need to do for refraction of waves, remembering that there will be a change in wave speed. Because of that, there will change in direction. In this case, from deep to shallow, it will bend towards the normal. From shallow to deep, it will bend away from the normal. Now wavelength will change as well. What we need to make sure that it's apparent that wavelength has decreased, moving to a shallow region. When it's going to a deeper region, the wavelength will increase. Coming to the last part on diffraction. Now, diffraction is something that probably is new to you. Now, let's just put that out right now. Diffraction refers to spreading of a wave when passing a gap. Right? So if we got a gap, it will start spreading. Now, we will be focusing on three aspects. Okay, angle of spread. You need to think about what does the front of or the center of the wave will look like. And lastly, thirdly, you must make sure that the wavelength remains constant. Right? Similar to reflection, wavelength will remain constant in this case. So now what we mean by diffraction of waves, again, is the idea of spreading. What I will, in terms of drawing the wavefronts now, we need to recognize there are two cases that's in your IGCSE syllabus. Now, case number one is when wavelength is much smaller than gap size. Right? So what I mean is this, you can see the gap is a lot larger than the wavelength. Now what we are looking for is, now what I can probably do right now is start by drawing dotted lines here. Draw dotted lines here. Now what we're doing here is actually this. We're trying to make sure that the small angle or spread. Okay. Now next, we want to make sure for this case we will need to have a flat front and wavelength constant. Okay, these are the three aspects that you need to make sure this is right. So wavelength constant. Now if I just measure this, again the wavelength seems to be 1 centimeters. So what I'll do is I'll just mark 1 centimeters, 1 centimeter, 1 centimeter. Alright. Now the flat front, what I'll do is I'll just draw flat straight lines here, straight line here, straight line here, straight line here. Alright. And just to add, the last bit is to make it spread slightly at the sides. And there we go. Now this is what we call as diffraction of waves. Waves that's traveling passing a gap, it will spread. Now, but because again in this case wavelength is a lot smaller than gap size, we have this we have wavefronts that look like this, very flat in the front with slight amount of spread at the sides. Okay, constant red, and also keeping the wavelength to be constant. Now moving on to the next case, case number 2, where wavelength is equal to gap size. Alright, now if you look at this, they're very close together. Alright, they're comparable. So what we're going to do is this. We're going to draw the wavefronts as well. Now the few things we're looking for is large angle or spread. We've got curved fronts, and lastly we got wavelength again remaining constant. Right, now let's just go through one by one. We go through large angle. Now earlier we had a small angle or spread. Now what we're going to do is spread it wider. Alright, let's just start with drawing dotted lines. This is just a rough guide. Okay, so we'll spread that far. Maybe it seems a bit asymmetrical to me, so let's just try to improve that. It probably will look something like this. Now next, Now before we go to the curved fronts, let's talk about the wavelength. Now again, looking at this, it seems like the wavelength is 1 centimeter. So right from here, let's just measure 1 centimeters. 1, 2, 3, 4, and 5. Right? So we have to keep the wavelength to be constant. That's why I'm marking that. Now I'm going to draw lines while the likewise is curved fronts. Now what we need to do is make sure that it's curved all the way. Right? Curved all the way. Curved all the way. Oops. I can go on to the next one. I think this is about 1 cm. So now this is what the diffraction wavefronts will look like. Again, we got two cases where wavelength is a lot smaller than gap size. We got flat wavefronts in the front with slight spreading at the sides. Whereas we've got case number 2, wavelength is equal to gap size. You look like Wi-Fi signals. Alright, so these are the three the aspects that we're looking for when you're drawing wavefronts of waves undergoing diffraction. We get back to our topic today, the topic of wave phenomena. Now we have gone through wave reflection, what reflection looks like. Again, remembering that we need to apply I must be equals to R, the law of reflection, and the wavelength remaining constant. Now refraction is where there's a change in speed. Remembering for water waves, it has to do with depth. Now when it's shallow, is where the waves are slower and where the wavelength will also be shorter as well. Alright, so we need to draw the wave fronts to reflect that. Now finally, diffraction is regarding to spreading around when it's passing through a gap. Now I got the three main aspects to look for in terms of, one is the angle or spread. Number 2 is the whether it's flat in the front or whether we curve all the way. And thirdly, for either case 1 and case 2, wavelength should be remaining the same. Alright, now we've spent some time practicing these drawings in class. Till then, see you and take care.